Hey everybody, how you doing? Happy Monday. Before I get started, I want to call it this a couple pieces of good news for you. And this is more if you're just struggling with what we're doing right now, because I feel throwing on reflections and translations at you at the same time, it's starting to get a little confusing. Our test isn't for 15 days, and I only have about another 4 or 5 more topics to teach you. So there's plenty of time to get caught up if you are getting stuck. Just don't give up. Just keep persevering, and moving forward. Second one is today was supposed to be the dilations lesson, but I looked and we could actually delay the dilations lesson by 1 day. So we're going to do the dilations lesson tomorrow. And all we're going to do today is introduce a new parent function, the absolute value parent function. And then after we learn about the absolute value of parent function, we're basically going to do the exact same things to this absolute value function that we did over the weekend. So there really isn't much need for many examples. Today we're just going to talk theory. The absolute value parent function, that parent function looks like this. Y equals the absolute value of x. And if we made a quick table of values, if you're thinking about, well, what's this graph look like? You could plug in 0, square root of 0 is, or not square root, absolute value of 0 is 0. 1, the absolute value of 1 is 1. 2, the absolute value of 2 is 2. 3, 3. This graph really looks a lot like y equals x. It goes through 0, 0, 1, 1, 2, 2, 3, 3, just like how you would expect y equals x to go. But it starts looking different when you get to negative values. The absolute value of -1 is +1. The absolute value of -2 is +2. The absolute value of -3 is +3. And if we graphed those points, -1, 1, -2, 2, -3, 3, we would get the exact same looking graph on the left that we do on the right, in terms of a nice straight linear line. But this is your parent function. And I included these 5 points, even though my table of values had 7. The parent function, we just need these 5 dots. 0, 0, 1, 1, -1, 1, 2, 2, and -2, 2. It's important for this fifth point, or the fourth and fifth point, the 2, 2, and the -2, 2. It's important because if you think back to our x squared graph, and our x squared graph, these 3 points looked exactly the same. So how can you tell the absolute value function from a quadratic function? And that's those points. Quadratic functions pass through 2, 4, and -2, 4. That's what makes them different. I always say that an x squared graph looks like the letter U, whereas an absolute value graph looks like the letter V. And that's our parent function for the absolute value. And then after that, the only thing you're going to be doing with this is graphing transformations and writing equations for graphs. So if you felt comfortable with that very long 30-minute lesson that I taught over the weekend, and you felt good about those examples, I don't think you need any more of this lesson. You should just go ahead and stop and call it a day, and you're in a good spot. If you did struggle with the weekend's lesson, well, these examples might help that out. So you might want to follow along some more. So let's say I wanted to graph this absolute value function, and it's 4 minus the absolute value of x minus 5. Now, I taught you guys last week that whenever you're looking at a function, you might want to look at it this way. You put all the function stuff first, and then this k out front. And if I wanted to try to get this function to resemble that, I would want to have this function information out front, so negative absolute value of x minus 5 in front, and then out back would be this minus 4. And now this graph, or this equation and this equation, they both have kind of that same look. Well, I have this negative out front, and according to our little guide here, this negative out front That means an x-axis reflection. This x minus 5 on the inside, that means that we're traveling 5 to the right. And this negative 4 on the outside, that shows that you're going 4 down. As I've been telling you guys in class, you must write this down when you're doing a graph. You must write down the transformations. Or, there's actually two different things you could do. You could talk about, you could make a list, or you could just physically tell me what happens with these coordinates. An x-axis reflection, that is affecting the y-coordinate, so it would create a negative y. There's no y-axis reflection, so x starts off the same. Then if you're going to travel 5 right, that means you're going to add 5 to all the x-coordinates. And if you're going 4 down, you're also going to subtract 4 from the y-coordinates. And if you make the list of transformations, just make sure that you list your reflections before your translations. So the work that you show must resemble one or the other. I prefer this way, and the reason I do is because then I could just take these 5 key points, negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2, and apply these 5 rules. I like to do it coordinate by coordinate. I find I'm less likely to make a mistake that way. So I'm just going to go with all the x-coordinates first. So negative 2 plus 5 is 3. Negative 1 plus 5 is 4. 0 plus 5 is 5. 1 plus 5 is 6. And 2 plus 5 is 7. Which makes sense. If you're just going to take the numbers negative 2 to 2 and move them all 5 to the right, they would still be in order, but just 5 to the right. Plug these in. Negative 2 minus 4 is negative 6. Negative 1 minus 4 is negative 5. 0 minus 4 is negative 4. Negative 1 minus 4 is negative 5. And negative 2 minus 4 is negative 6. And then I could just graph. And I know that this graph is with this x-axis reflection is simply going to be this downward shaping, downward facing absolute value graph. And then the 5 key points, this middle point, the 0, 0, became 5, negative 4. The 1, 1 point became 6, negative 5. The 7, negative 6 point. And then 4, negative 5. And 3, negative 6. Okay, that's how you'd want to go about doing this problem if you were not using graph paper. If you were using graph paper. Oh, wow. Okay, so if I was using graph paper, I'd probably do it this way. If I take the point 0, 0 and I do an x-axis reflection, it would still be at 0, 0. But then if I went 5 to the right, 1, 2, 3, 4, 5, and 4 down, 3, 4, I would then be there. And then, I don't know, when you think about it, if the parent points go like this, and there's an x-axis reflection, once you have this coordinate point, it would logically follow that the other 2 points would work like this, as long as there isn't a dilation. And that should work out. But you're using graph paper, so you need to use your straight edge. And that would work like that. So it's kind of common sensing your way to it. Or if you continued upon just the using the reflections, say if I took this point 2, 2, if I did an x-axis reflection, that would bring it down to here. Then if I went 5 right, 1, 2, 3, 4, 5, 4 down, 1, 2, 3, 4, I end up with that exact same dot. So you just go to all 5 of these points, perform your reflection, go 5 right, 4 down, and you'll end up at these same points that we had here. So that's looking at the same problem twice, once using graph paper, once without using graph paper. Whichever way you're most comfortable with is the way that I want you to do it. If I had a choice, I would ask everybody to learn it this way. It is more mathematically precise. And once I put in dilations into this, it's going to be really obvious why Elliott prefers this technique when graphing. Finally, I have one more example, and it's a find the equation problem. And let's say I had this graph right here, and the instructions were to find the equation. All right. Well, this problem's pretty similar to the last one. Well, I guess it's a backwards problem. You first want to look for reflections when you're trying to come up with an equation. And with reflections, you really need to be able to look at the graph and just based off its look, know what type of reflection is occurring. Normally, our absolute value function is an upward-facing V. This one's a downward-facing V. So that is our vertical reflection, a x-axis reflection. And then think about this key point right here. If you took 0, 0 and reflected it over either axis, it doesn't matter. It would still reflect to 0, 0. After that, you can then just see, well, after you reflected it and it's now this downward facing absolute value graph, what did it do to get from here to this start point? And I went 1, 2, 3, 4, 5. Did I count that right? 1, 2, 3, 4, 5 to the right and 2 down. And everybody make sure that when you're writing these problems that you actually do write out the transformations and the entire list of them. All right, now use this as your guide. When we have an x-axis reflection, that's going to be that positive negative out front of the function. So in my final answer with that negative out front, I would have y equals negative, then the function, and this is an absolute value graph, so absolute value of 5 to the right. We put that into the equations by going x minus 5, opposite of what makes sense. Outside, you do exactly what you're supposed to. So if you're going to go 2 down, that would be like you're going to subtract 2. And once again, just using this as a guide. When it says x minus h, that's a translation of h unit. So it's going right 5, so just x minus 5. The down 2, it's normally plus k for a vertical translation of k units. So if it's going down, you would actually subtract, so the minus 2. So that's finding the equation of. Okay, students, if these two examples, if you found them rather confusing, I would strongly recommend going back to this weekend's lesson. I know it's 30 minutes long, but it has 6 really good examples in it using both graph paper and non-graph paper to show you both techniques. And other than that, that's it for this parent function. And then, so tomorrow, Tuesday, we'll spend one more day looking at just reflections and translations, but we'll apply them mostly to this function here, which gives you a little bit more time. So if you're still struggling on reflections and translations at the same time, go back, watch some of those videos maybe, try out some practice problems, and then see if you can get all those questions answered tomorrow, because tomorrow night we're going to add in the next transformation, which is dilations, and then then these problems get complicated. After that, though, we're going to have pretty much 2 to 3 days of straight practice with very little video watching, because this is going to be a lot of practice, a lot of helping each other out, and that's it. So have yourselves a great night, and I'll see you tomorrow, everybody. Bye-bye.